Combinatorics is a branch of mathematics that deals with counting the number of ways to choose or rearrange a group of items. With all the formulas and all the different situations to think about, it's easy to get confused. But what if I told you there is a quick and easy way to remember all the combinatorics formulas? Would you believe me? And what if I told you that to tackle the most common combinatorics problems, all you need to learn is a simple card game? Well, you'll find all of that in this video. Ready? Let's get started. Let's start with a deck of blank cards. You can pick as many as you like, but I've chosen 5. Now, let's personalize them with different drawings. I go with a tree, an ice cream, a heart, a star, and finally my student's favorite. They always draw it on the board. I mean, who doesn't like cherries? All combinatorics problems boil down to answering this question. In how many different ways can you draw k cards from a deck of n cards? We'll follow the example where we draw k equal to 3 cards from a deck of n equal to 5 cards. Before we start, we need to decide on 2 rules, 2 game options. The first game option, which we can turn on or off, is whether or not we are allowed to draw the same card more than once. If we turn this option on, every time we draw a card, a new copy of that card gets put back into the deck. This means we can draw the same kind of card multiple times. With the option turned off, each card you draw is removed from the deck and cannot be picked again. In this case, the number of cards you draw can never be more than the total number of cards, because after n draws, the deck runs out. The second game option is about the order in which we pick the cards. If this option is on, choosing tree, star and ice cream is different from choosing star, ice cream, tree, because the order of the cards matters. On the other hand, if the option is off, you don't have to pay attention to the order in which you draw. What matters here is the set of cards. To sum up, for solving combinatorics problems, we need to learn how to count the number of ways to draw k cards from a deck of n cards in each of the 4 possible rule sets you get by turning on or off the repetition and the order option. Each of these 4 cases has a technical name in combinatorics, but we'll get to those later. The first goal is to learn the formulas, and we'll do that with this trick. Let's build a coordinate plane where the horizontal axis shows repetition. Positive means the option is on, negative means it's off. The vertical axis shows order. Again, positive means the option is on and negative means it's off. To help you remember, keep in mind that we put the order option in the vertical axis, which is also called the ordinate. Each of the 4 quadrants represents one of the 4 rule sets of the game, and we'll put the corresponding formula inside each quadrant. I hope you will appreciate that the comparisons between these formulas matches the directions of the axis. I mean, there are definitely more ways to pick cards if you're allowed to repeat your choices. And similarly, you have more ways to make choices if you also consider the order you pick the cards. Most of all, I hope you like that the way to easily find these formulas follows the usual order of the quadrants, from the first to the 4th. Remember, the first quadrant is in the top right and the counting goes counterclockwise. Let's start with the first quadrant. We turn on both repetition and order. That means when we draw a card, it goes back into the deck and can be picked again if we want. We'll consider the order in which we pick the cards. How many different selections can we make with these rules? Let's think about it. For the first draw, we have 5 choices. Then, for each of those choices, we have 5 choices for the second card, and for each of those, another 5 choices for the third card. So 5 times 5 times 5 gives 125 total selections. With the same reasoning, we can say that the general formula for counting the number of different selections in the first quadrant is n times n times n times n k times. namely n to the k, simple and easy to remember. Now let's move on the second quadrant. The second quadrant is similar to before, but this time repetitions are not allowed. That means once we draw the first card, we cannot draw it again. So after n choices at first, there are only 4 left for the second pick, and 3 for the last one. In total, 5 times 4 times 3 equal to 60 possibilities. In general, the formula to count the different selections is n times n-1 times n-2 and so on, multiplying k numbers in total. To make this formula for the second quadrant easier to remember, you can use this alternative notation with factorials. The factorial of a number is shown with an exclamation mark and is defined as the product of that number and all the natural numbers before it, down to 1. For instance, 4 factorial is equal to 4 times 3 times 2 times 1. By convention, 0 factorial, which doesn't fit the previous definition, is set to 1. Now that we have the formula for the second quadrant, let's get ready to move on the third quadrant. Here, repetition are not allowed, and the order of picking doesn't matter. It's kind of like drawing the cards all at once. Outcomes like heart, tree, star, and tree, heart, star, which counted as different selections before, now count as the same set of cards. Precisely, 6 of the previous sequences now count as the same set of cards. Why 6? Because it's like counting the ways you can arrange the cards in the set made up of heart, tree, and star. In the previous quadrant, we saw the formulas is 3 factorial, which is equal to 6. This means we no longer have 60 different selections like before, because groups of 6 now represent the same set of cards. So we have 60 divided by 6, which is 10 different selections. In general, since the number of ordered selections is n factorial divided by n minus k factorial, then the unordered ones are found by dividing that by k factorial. And here is the formula for the third quadrant. In this case, there's a compact and widely used notation to make it easier to write. The formula n factorial divided by n minus k factorial times k factorial is written more simply as n choose k, a bracket with n on top and k on bottom. With that said, we are ready to move on the fourth quadrant. The formula for the fourth quadrant can seem tricky, but it's easier if, as done before, we build on the previous quadrant. Now, unlike before, each card can be drawn multiple times. Anyway, the order of picking still does not matter. Before we look at the formula, here is a hint. With these rules, there are 35 different ways to select 3 cards from the deck, and here you can see them. To relate this pattern to the previous case, let's try replacing the repeated card that you can see highlighted in red with extra cards that aren't in the original deck. Since some selections have 2 cards to replace, I'm adding 2 new cards, the ostrich and the sunglasses. So we can swap out the duplicates. And look at that, can you notice something? Well, what you see here are exactly all the sets of 3 cards drawn without repetition from the deck expanded by these 2 new cards. This is shown by the fact that all the sets you see are distinct, and according to the formula from the third quadrant, the total number of combinations is 7 choose 3, which is exactly 35. What did we get? We got that, when order doesn't matter, to count the number of ways to draw k cards from a deck of n cards with repetition allowed, we can instead add k minus 1 cards to the deck and count the ways to draw k cards without repetition. Amazing, isn't it? The proof of that works like we saw before, by replacing the repeated cards with new extra cards. The replacement has to be done carefully. For example, if in star heart heart we replace one heart with an ostrich, then in star star heart we cannot replace a star with an ostrich, or else we'd repeat the same previous set of cards, so we'll use sunglasses. Building on the formula for the third quadrant, we found that the formula for the fourth quadrant is n plus k minus 1 choose k. The chart is complete. Let's review the technique to build it. In the first quadrant, we have k times n choices. In the second, cards are not replaced, so each draw subtracts one option for the next one. In the third quadrant, we ignore the order, so we divide the previous formula by k factorial to account for the repeated selections with the same k elements. And in the fourth, we deceive repetitions by applying the previous formula to a deck expanded by k-1 extra cards. Regarding the common terminology in combinatorics, selections where the order matters, the top quadrants, are called permutations, while selections where the order doesn't matter, the bottom quadrants, are called combinations. So we have permutations without repetition, also just called permutations, and permutations with repetition, along with combinations without repetition, also just called combinations, and combinations with repetition. To help remember, notice that permutations starts with a P for podium, which reminds us of ranking and order, while combinations starts with a C for circle, which reminds us of a group or set of objects. Also, because of these initials, a common notation for the formulas is the one you see here. It uses P for permutations and C for combinations. The asterisk means you are allowed to repeat a draw. Before doing exercises, we need to talk about a fifth and final special case, anagrams, also called permutations of multisets. This is the case where we draw as many cards as are in the deck, k equal to n. We care about the order of the draw, and the cards are not replaced. You might say, we already covered this case in the second quadrant, and I'd say, yeah, but this time the starting deck doesn't have to be made of different cards. There can be identical cards. So does that mean we have to rethink of all the four previous cases when the starting deck can have repeated cards? Luckily no. In the two cases where repetitions are allowed, having extra copies in the original deck doesn't make a difference. In the other two cases, the formulas get more complicated, so it will be more practical to break the problem into simpler chunks that we can solve one by one with the formulas we already know. This can be done for anagrams too, but it's worth facing them once in your life. So let's dive into permutations of multisets, that is the different ways to reorder decks with repeated cards, like these ones. If all of the 7 cards in the deck were different, we'd have 7 factorial permutations. But here, some cards are identical. There are 3 factorial ways to rearrange these 3 star cards and 2 factorial ways to rearrange the 2 heart cards. Using the same reasoning we saw in the third quadrant, we can conclude that the total number of rearrangements is 7 factorial divided by 3 factorial and 2 factorial, which gives us 420. These kinds of repeated permutations are also known as anagrams, because they let us count how many different ways we can shuffle the letters of a word, even if it doesn't form a real word from the dictionary. The general formula to count the number of anagrams of a word with n letters is divide n factorial by the factorial of the number of times each repeated letter appears. Namely, you take n factorial and divide it by k1 factorial times k2 factorial times k3 factorial and so on, where k1, k2, k3, etc. are the counts of each letter that appears more than once. With this formula, our combinatorics framework is complete and looks like that. Now we can finally see how to apply it together with our card game to solve problems. First exercise. We've forgotten the 4-digit code to open our safe. Here is what we do remember about it. It's exactly 4 digits long, each digit is odd, and no digit is repeated. How many different codes could match these conditions? So, how do we solve this? Creating a security code means lining up a sequence of symbols that, according to this exercise, are just the n equal to 5 odd digits. It's like having a deck of digits to draw from. We'll make a code by choosing k equal to 4 of them. Now let's ask ourselves, are repetitions allowed? In a generic code, yes, but in this exercise we know no digit repeats, so repetitions are not allowed. Then, is the order important? Well, in codes, the order of the digits matters a lot. So, we are in the second quadrant, permutations without repetition. The formula to calculate this is n factorial divided by n minus k factorial, which gives us 120 possible codes, and that's the problem solved. Second exercise. We went to a towel shop because the world is about to end. We are going to buy 4 towels because that's all fits in our suitcase, and the shop sells 8 red towels, 4 blue towels, and 6 green towels. How many different combinations of towels can we leave the shop with? We have 3 types of towels: red, blue, and green. Let's start by asking, are repetitions allowed? Even though the towels aren't infinite, there are always enough of each color to repeat a choice as many times as we want. Does the order matter? I'd say no. Even if we shuffle the towels around the suitcase, the set of towels we bought is the same. So we have a deck of n equal to 3 cards, and we are choosing k equal to 4 of them, with the repetition allowed and order not counting. This is the fourth quadrant, combinations with repetition. The formula is n plus k minus 1 choose k, that gives us a total of 15 different ways to fill the suitcase. Third exercise. Ready? This is a real-life problem. During a trip, a group of 9 students need to be divided into 3 hotel rooms. The first room has 4 beds, the second has 3 beds, and the last one has 2 beds. In how many different ways can we assign the students to the rooms? If you want to think about it yourself, just pause the video now. Otherwise, keep listening. We might wonder how to build a deck of cards. Is it better to create a deck where the cards represents the 9 students, or a deck where the cards represent the 3 rooms? Well, both approaches work. If the deck represents the students, we need to pick them to fill the rooms one at a time. We start by filling the room with 4 beds. We must choose 4 students, order doesn't matter, and students cannot be chosen more than once. This is a combination without repetition, giving us 126 possibilities. Once this room is filled, 5 students remain to be assigned. Then we fill the second room. There are 10 ways to select 3 students for this room, and the remaining 2 students goes to the third room in the only possible way. For each of the 126 ways to fill the first room, there are 10 ways to fill the last 2 rooms, summing up 1260 possible combinations. Quite a lot. How the teachers always manage to find the worst combination is still a mystery. Anyway, this problem has a second, more direct solution. Let's build a deck made up of 4 cards representing the room with 4 beds, 3 cards representing the room with 3 beds, and 2 cards representing the room with 2 beds. Then we line up the students and randomly hand out the cards to assign them to the rooms. This makes it clearer that counting the ways to distribute the students among the rooms is equivalent to finding the anagrams of the original deck. The formula for anagrams is 9 factorial divided by 4 factorial, 3 factorial, 2 factorial, which equals, guess what? 1260. I hope you not only enjoyed the video, but also found it helpful. If you think more videos like this one could support you in the future, please give a like and subscribe to the channel. Let me know in the comments if there's a topic you'd like help with. Thanks a lot, and meanwhile, don't panic.